Okay, so let's start our today's class. In today's class, we are continuing with particle kinetics, which is basically the second half of our dynamic course. Okay, so before going into it, let's discuss that what is basically impact. So in engineering mechanics course, impact is usually referred to a condition. Uh, okay, let's me specify that what we are going to study in today's class. So in today's class, the first topic that we are going to cover that will be impact, and with impact we are going to discuss the coefficient of restitution, how both of them are basically connected, or how both are interrelated. Okay, so in our course, that is in engineering mechanics, impact is basically refer to a condition where two bodies comes in contact, or in other word we can say when two bodies collide into each other during a very short period of time, and they exert a very large impulse force onto each other. So as a result, their momentum as well as the corresponding velocity changes. Now, how that impact causes change in velocity, that is basically characterized by the coefficient of restitution. So we can say this is like the property of material, right? So to understand this example, or to understand this concept of coefficient of restitution, we can have example from our daily life. Let's have an example from one of the sports activity. Let us consider uh, tennis sport. So for example, in tennis, players must take into consideration the type of court on which they are playing. For example, they must look, or they must consider that on which type of court they are playing, whether it's a grass type, it's a carpet court, or it's a clay court. Because different tennis court will have different bouncing, means the surface will react differently to the bounce. And definitely, this is because of coefficient of restitution between the two colliding material, that is between the ball and the court surface. So if you are playing on a different surface, if even if you consider a cricket match, so the type of pitch on which you are playing, that will basically decide that what type of bounce, what type of swing you can have, right? So that is due to the coefficient of restitution between these two contacting material, or that the two contacting bodies. Okay, so let us consider two objects. This is object A and object B. So sometime I will consider, I will use this word body, sometime I will use object, sometime I'll be use particle. So all of them are basically having same meaning. Okay, so let's say this object one is having mass 1, or let's say it is having mass A, and the other one is having mass B. Both objects are having some velocity, means both are carrying some momentum, and they are coming towards each other, and finally they come in contact, or in other word they collide, right? So the plane where they come in contact, or where they collide, that plane is basically known as plane of contact, and the line perpendicular to this plane of contact is basically known as line of impact. Okay, kindly give me a few seconds, I have a call. Okay.
Okay, 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 okay.
Okay, so let's come back to our class. So the plane where both these particles come in contact, that plane is basically known as plane of contact, and the line perpendicular to this plane is known as line of impact. Okay, so if the particles means, if this line of impact and the particle velocity, if both are in same direction, or if both of them are parallel, in that case the impact that we will be having will be known as central impact. But if the velocities and the line of impact, if they are having certain angle between them, means if the angle is not 90-degree, if it is some other angle, so in that case the type of impact will be known as oblique impact, right? Okay, so initially we were having two particles, they were coming together with a certain momentum. When they come in contact, so after the contact, the question arises, the question arises that what will be the velocity of both particles or both bodies after the impact. So in this case, if you observe this system, so we are having two particles, this particle A and particle B, both are having their own momentums and moving with their own momentum. There is no external force acting on these particles, means there is no impact from outside. So if there is no impact from the outside, this means we can apply conservation of linear momentum. And what is the conservation of linear momentum? The total momentum before and after collision, that will remain conserved. So the momentum of particle A initially plus the momentum of particle B initially, that should be equal to the summation of momentum of particle B and particle A after the collision. But if you observe here, we are having two particles and we want to find out the velocity VA2 and VB2. So for means, in other words, what I can say, what we can say, that actually there are two unknowns. There are two unknown, but we are having this single equation. So it is not possible to find out these two unknown with a single equation. But on other hand, we are having another equation. We have another term which we just defined, that is the coefficient of restitution. Okay. So if we write equation for coefficient of restitution, that will be given by this equation. So what this equation basically says, or how we can define this equation, we can say this is the ratio of velocity difference after the collision to the velocity difference before the collision. So coefficient of restitution is basically the velocity difference after, that is VA2 and VB2, the difference of these two, and before is basically the difference VA1 and VB1. So the word before basically shows the state before the collision, and the word after, which I use, that is basically for the state after the collision. Okay, remember one thing, if you write this one VB2 minus VA2 in numerator, so what you can do in denominator, you need to replace this term. For example, over here we are having VB2 minus VA2. So what you need to do in denominator, you need to write this VA on the left side, and then you need to subtract VB from it. So this is one thing that you need to remember in this equation. Remember, it's basically the ratio of velocity difference after to the velocity difference that the particles were having initially. Okay, so coefficient of restitution. So coefficient of restitution, like coefficient of friction, it is determined experimentally, and definitely it is between the two colliding material, and generally its value is from 0 to 1. So if the value of coefficient of restitution, which is represented by E, if it is 1, that means we are having elastic impact. Elastic impact means after the impact, both objects or both bodies can come back to its initial position. So in this case, there will be no energy loss, and the relative separation velocity equal to the relative approach velocity of particle. But this thing is only possible in theory. Definitely in actual case there will be loss of energy due to that impact. So in this case we are considering that there is no loss of energy in form of noise, in form of heat, in form of deformation, or due to any other reason. Okay, then we are having plastic impact. In plastic impact there will be some permanent deformation, and in case of purely plastic impact, the value of coefficient of restitution E will be basically 0. In that case, the relative separation velocity is 0, means the objects stick together after the collision, and then they move with a common velocity. And in this case, the energy loss will be maximum. So usually, in example or in problem, the coefficient of restitution value that you will observe, it will be between 0 to 1. Okay, sometime in literature, you may come across the coefficient of restitution value greater than 1. So now the question arises that how it can be greater than 1. So in certain scenario, when two objects come in contact, and during that contact, if some chemical reactions occur, so due to that chemical reaction, uh, the value of E can be greater than 1. But usually under normal condition, the value of E, that is coefficient of restitution, that will be between 0 and 1. Okay. Now to further strengthen our concept, let's have an example. So this is basically example of oblique impact. We are having two balls, or we are having two spheres, or two particles, or two objects, and both are coming in contact. And remember, the plane of contact, it is inclined to horizontal with an angle of 45 degrees. So let's see what we have in this example of oblique impact. Two balls with masses and speed as shown collide into each other. Their plane of contact is at 45-degree angle with the horizontal. Now determine their respective speed after the collision. What we need to do, we need to find out their respective speed, that is VA2 and VB2. If the coefficient of restitution is 0.5, so what I told you, that E that you will observe during problem, it will be between 0 and 1. So over here we are having that value 0.5. So the plane of contact in this case, this is basically inclined, and the line of action in this case, it will be perpendicular to this one over here. Okay, so let's draw our free body diagram. So the line of impact, this is the line of impact which is perpendicular to the plane of impact. Okay, and the plane of impact is making an angle of 45 degree. So both particles were having initial velocity VA is equal to 3 meter per second and VB is equal to 5 meter per second, right? The velocity will remain same. Okay, let's define our coordinate axis. So let's the line of impact is along the x-axis, and perpendicular to it, let it be the y-axis. Okay, so now in this case, if we look at the line of impact, so with the line of impact, the velocity are making certain angle. So it can have two components, right? This is 45 degree and this is also 45 degree. So one will be cos and one will be sine. Similarly over here, we will be having two components for velocity. Okay, so let's try to find out those components. So these are basically the component along y-axis, and this is the component along x-axis. This is the component along x-axis for B, and this is the component along y-axis for B. Okay, so from basic trigonometry, if you want to find out the value of VAX, so since the angle over here, if this angle is 45, so this component will be with sine. So VA1x, that should be equal to VA sine of 45, and VA is 3, so 3 sine of 45, From here you can find out value of VA1x. Similarly, you can find out value of VA1y, VB1x, and VB1y. Okay, so we have found out the components of both velocities, that is VA1 and VB1, x component as well as the y component. So if you observe this diagram, the impact over here, the impact between the two particles, this is along the x-axis. So we can apply, we can apply this conservation of linear momentum along the linear axis. So according to conservation of linear momentum, the momentum for particle A plus the momentum for particle B before the impact should be equal to the momentum of particle B and the momentum of plus momentum of particle A after the impact. Similarly, we are also having the coefficient of restitution that is equal to 0.5. So by writing the respective equation and by using these two, what we can get by utilize these two equation, we can find out VA2x and let me remove this one. And VB2x, right? So from here, the two unknowns in this equation, this was the noun one, this was the noun one, this was unknown, and this was unknown. So by using another equation in which again we are having, this is the unknown and this is the unknown. So we were having two equations and two unknowns. So by utilizing both of these equations, we find it out VA2x and VB2x. So this is basically the final velocity x component. Now we need to find out the y component to y. So if we get these two, then it will be easy for us to find out the final velocity. So let's look at it. To find out the y components, what we can do, we can apply principle of linear impulse and momentum. Okay, as we know that principle of linear impulse and momentum, it can be given by the equation that is momentum before plus the impact that should be equal to the momentum after. Similarly, we can also write this equation for particle B, momentum before plus the impact that should be equal to the momentum after, right? So in this case, if we look at whether there is any impact in the y direction, if you look at this diagram, so along the y direction, there is no impact. So this means what we can do, we can cancel out this impact term. So when you cancel out this impact term, what you will get, MAVA1y, that will become equal to MAVA2y. And similarly, the MBVB1y, that will be equal to MBVB2y. So what this indicates, that the y component of momentum before as well as the y component of momentum after the collision or after the impact, that will remain the same, right? Since there is no external impact. So by doing so, what we will get the value of VA y component after the collision as well as the value of VB y after the collision. So now we got VA2x and VA2y and VB2x and VB2y. So by combining, okay, I think I have missed one of the slide. So what we can do over here, now you are having VA2x and you are having VA2y. So if you take its square and take its square root, so what you will get VA2, right? And similarly, VB2 will be equal to VB2x square plus VB2y square. By doing so, you will get this VA2 and VB2, and this is basically the required components which was asked in the question, or this was basically the required values for which we were doing this problem. So this is basically determine the respective speed after the collision if the coefficient of restitution is known. So if you put these values over here and also in this one, so what you will get, you will get the required unknowns. So I hope this thing is clear. Is it clear to everyone?
Yes, sir.
Yes, sir.
Okay, if it is clear, then let's move forward. Okay, this is an example. You need to go through it. uh, the answers are given, so you need to select one of the answer, the best answer, or the one that is closer to your answer. Okay, so the suggested problem are basically again from RC Hivler. So examples are 15-9 to 1511, and then again you need to look into the relevant problems and need to solve those relevant problems. Okay, so let's go through angular impulse and momentum. But before this, let's have a break for a minute. हेलो जी, आवाज आ रही है आप लोगों को?
Yes, sir, are you?
Okay, so sorry for delay.
Yes, sir.
So okay, so let's go to angular impulse and momentum. So before going or before understanding angular impulse and momentum, let's recall a few topics from our statics, especially the moment. So if you remember what we studied in our static course, the moment of force uh, that we learned, it was basically we can say the rotational effect caused by the force about a reference point, or we can say it's about an axis that passes through some reference point. So in scalar form, the moment is calculated by the magnitude of force multiplied by the moment arm, which is actually the perpendicular distance from the reference point to the line of action of force. And over here, if you look, this is the moment, this is the force, and this is basically the moment arm. So if this is the applied force, let's say this D is the moment arm, and if you want to find out, this is the force, we want to find out moment about point O. So the perpendicular distance between the line of action of force and this reference point, this is basically the dr moment arm. So if you multiply this one and this one, so what you will get basically the moment about point O. So in scalar, we can just simply get it by multiplying the force with the perpendicular distance or with the moment arm. Okay, in vector form, how we can get moment? It can be calculated by the cross product of position vector to the force vector. That is position vector, and this is the force vector. So for example, if we are having force, we want to find out the moment about any point. So what we can do, we need to find out the position vector r, this position vector r, and we also need the force vector. So what we can do, we can take cross product of both these vector, and we will be able to find out the moment vector, right? So what we remember or what we studied, that the position vector from start must start from the reference point, and it can end anywhere along the line of action of force. For example, it must start from the reference point, and it can end anywhere along the line of action of force. So if it is clear to you people, then let's discuss the angular momentum. So angular momentum, what we can do, instead of angular momentum, for example, okay, we will replace this m about O with the angular momentum about O. So the angular momentum will be represented in this lecture with h, and instead of force, since the moment is due to the momentum now, this will be replaced by mv, and we will take its dot product, and this force will be replaced with mv, right? So the moment or the angular momentum about point O, that can be given as momentum and its dot product with the moment arm, right? Okay, in vector form, what we can do, again in previous slide, in this slide, we will replace this f with mv. Over here, this will be ho. Ho means angular momentum about point O, and in vector form, so that will be the cross product of vector r cross, instead of f, we will be having momentum. So this is basically the angular momentum in vector form. Okay, so similar to the principle of linear impulse and momentum, which was mv1 plus the impact term that was equal to the final momentum. So principle of angular impulse and momentum, it will be written in the same way. So instead of linear momentum, what we will write, h naught 1, that should be equal to h naught 2. But if there is some applied angular impulse, we need to consider it. So the initial angular momentum plus the angular impulse, that should be equal to the final angular momentum. And this is the principle of angular impulse and momentum. Okay. Again, let's make an analogy to the static course. So condition for rigid body equilibrium, if you remember what we were studying in that the summation of force acting about any point, that should be equal to 0, and the summation of moment should also be equal to 0. The summation of all forces should be equal to 0, and the summation of moment about some reference point, that should also be equal to 0. That was basically the condition for rigid body equilibrium. So if you want to write it in scalar form, this is basically the vector form. If you want to write it in scalar components, so what we can have for 3D case, we can have three component of force, that is fx, fy, and fz. Similarly, we can have three component of moment, mx, my, and mz. So we can get three equation for forces and three equation for moment. That is summation of forces along x, summation of force along y, summation of force along z. All of them should be equal to 0. Similarly, the moment about x, the moment about y, and the moment about z, all these three should also be equal to 0. If you are having a 2D problem, so in that case, you can write summation of forces about x-axis, summation of forces about y-axis, and the moment about any certain point, that should be equal to 0. So in 2D case, we will be having three scalar equation, whereas in case of 3D problem, we will be having six scalar equations. Okay, so if we consider the principle of impulse and momentum, in that case, we are having two equations, that is summation of means if we compare it with the previous one, over here we were having the resultant force was equal to 0, and in this case the resultant moment was equal to 0. So we were having two equations, and if it was 3D system, so in scalar form we were having six scalar equation. Now in this case we are having two equations, one equation, this is the second equation, and if you want to write it in scalar form, or if you want to write down its scalar component, so we can have six scalar equation. But if you are having 2D, so like the previous case, we will be having three scalar equation. So let's discuss these three scalar equation only. That is the linear principle of linear impulse along x-axis, principle of linear impulse along y-axis, and the principle of angular impulse and momentum. These are basically the three equations that we got for principle of impulse and momentum, especially if you are considering the angular impulse and momentum. Okay, since we got this equation, what this equation says? This equation says that the angular momentum before plus the angular impulse, that should be equal to the angular momentum after, right? So this is known as the principle of angular impulse and momentum. Now, if we remove this term, that angular impulse, means if there is no angular impulse, this means this term should be equal to this one. This one will become equal to this one, and this one will be known as conservation of angular momentum, in which the angular momentum before and after the process or after the impact will remain the same. Okay, if you are having more than one particle for a system of particles, and remember, if there is no net external impulse, or if there is external impulse but that is negligible, as I have given you example in our previous case or even in our previous class, means for example, let's have an example again, that same example. If you want to apply force on a pin, right? So the force that you are applying, or the external impact and the weight of hammer, that is much more as compared to the weight of that pin. So if that pin, if that pin, if you want to consider the weight of that pin, so that weight pin is almost negligible as compared to the external impact on it, right? So in that case, what we can do, we can neglect the weight of that pin, because the remaining forces or the remaining terms that we have in that system, it is much more. So in that case, that force or that weight force, that can be non-impulsive. But when it will be not impulsive, if we compare with the external impact that the hammer is applying on the pin, right? Okay. So for a system of particle, the summation of all moments before should be equal to summation of all angular momentum after the process. Now to understand this thing, again, let's have an example. A 2 kg ball is connected to a string and is moving with the horizontal plane. If the force in the string F pulls the string in so that its length is a function of time as shown, determine the speed of ball when t is 5 seconds. What we need to do, we need to determine the speed of ball. Okay, what they are saying, this is fixed point and we are having a ball that is connected to this point, and over here we are having this string, and the length of string, it can increase and decrease, and the length or the radius of that string can be given by this equation. R is equal to 20 minus 2t. For example, at any instant, if you want to find out the radius that the ball is following, you can put that second. For example, at t is equal to 1 second, put t is equal to 1 second, you will get the radius. At t is equal to 5 seconds, put it over here, you will get the radius. So the mass of ball is 2 kg. It is connected to a string and is moving with a horizontal within a horizontal plane. It is moving within a horizontal plane. So if it is moving within a horizontal plane, this means we can neglect its self weight, yeah, its own weight, or the support weight in this case, or the support force. Its length is a function of time as shown. Determine the speed of ball when t is equal to 5 seconds. What we need to do, we need to find out the speed of ball when t is equal to 5 seconds. Initially, the ball was given a velocity of 10 meter per second. So the initial velocity is 10 meter per second. And remember, since the ball is moving some curved path, so we can have Vr and we can have V theta. So initially, it was given this velocity, definitely that V1 must be equal to V1 theta, right? And after time t is equal to 5 seconds, so it will be having two components, Vr and V theta. So Vr, it will be along, sorry, V theta will be along the direction like this one, and V theta will try to pull it outside or towards the center. It can be in any direction. Okay, so in second half, what they are asking, what is the total work done by the force during this process, right? Are you getting this question? What they are asking in the question? समझ आ रही है कुछ?
Yes, sir.
Okay. So let's draw its free body diagram. As over here, they shown that string is moving within horizontal plane. So if we draw free body diagram for the particle within the horizontal plane, so the only force that will act on the particle, this is basically the force that the string have, or which the string apply on this particle. Okay, this particle is moving in some curved path, right? And at any instant, if you look this force, the only force which is acting on this particle, this is along this line, right? So due to this force, if you want to find out moment about point O, the moment will be 0. Why? Because there is no perpendicular distance between this force and this point O. So means, according to principle of transmissibility, if we move the force over here, so the force is actually acting at this point. Means we can move the force along the line of action of force, or in other words, we can say if it doesn't have any other component, the moment about point O due to this force will be 0 because it doesn't have any other component. Okay, so the summation of moment due to all forces, that is equal to 0. If the moment is 0, this means the angular impulse due to the moment, that should also be equal to 0. Okay, so if the angular impulse is zero, this means we can apply conservation of angular momentum. That is the angular momentum before and after the process, that should be the same, right? Okay. So as I have told you, we need to use the r theta component. So let's say the r theta coordinates. So let's say this is the r, the radial component. This is the theta component. Okay. So velocity will be having v theta and vr. So this one is basically momentum into moment arm before, that should be equal to momentum into moment arm after, right? So momentum before is given by mv1, momentum after, that can be given by mv2. But mv2 again, it can have two components, but the momentum that it have along this radial one or along this direction, it is due to this v theta 2. Okay, what is r1? R1 is basically the radius, and we know that for r we are having this equation, that is r is equal to 20 minus 2t. R is equal to 20 minus 2t. So at t is equal to 0, it will be having one value. At t is equal to 5 seconds, the value will be changed. So r is equal to 20 minus 2t. It is given by this one. So r1 means when we were having t is equal to 0, r1 will become 20 meter, and at t is equal to 5 seconds, the value of r2 will become 10 meter. And remember, v1 was 10 meter. So if you have this value, this value, this value, this value, and this value, what we can do? We can find out v theta 2. So v theta 2 is 20 meter per second. But we know that we can find out the radial component, and the radial component can be given as the temp derivative of r. So dr by dt, it will give us the vr. Since we have this r equation, if you take dr by dtt, you will get this vr component, and that should be equal to minus 2 meter per second. So now we are having v theta 2, we are having vr, put it in this equation, and we will get the final velocity or the final speed. So determine the speed of ball when t is equal to 5 seconds. This has been identified. Now what they are asking in the second half, what is the total work done by F during this process? So for work, what we can do, we can use principle of work and energy. So according to principle of work and energy, the work done during the process due to the force, that can be equal to the change in kinetic energy, right? So this is m, this is given, this is given, v2 is given, v1 is given. By putting the values, we can find out the work done by F during this process, right? So this was the two things that was required in the problem. The first one was the speed of ball, and the second one is basically the total work done by the force during this process. Okay, so again, here is a problem. You can kindly go through it, and the answers are given. So you need to select the one that closely resemble your answers. Again, if you have any question, you can ask me, you can email me, or you can type on Google Classroom. Okay, so the relevant example again, it's 1512 to 1515. The one that I did over here, that is basically very much similar to 1514. In 1514, only the units will be changed. Remaining example is same as the one I have done in the class. And then again, you need to look for the related problems. Okay, so this is the end of second portion of our today's lecture. And with this, I'm also going to end this lecture. So if you are having any question, you can ask. जी
Thank you,
क्वेश्चन
sir.
है कोई? Okay.
No, sir.
Okay, so let me put the recording off.